Hello everyone. Today we're going to talk about another new topic. Do you know what it is? It's steam auto control valves. Welcome to our program today. Steam auto control valves, the hidden heroes of industrial power. Section 1, the power of steam. Before we get into the control valves, let's understand what they are controlling. Steam is not just hot water vapor, it's stored energy waiting to be released. When water boils and turns into steam, it expands to about 1,600 times its original volume. This expansion creates tremendous pressure, the force that once powered the Industrial Revolution and still drives much of our world today. Steam has an energy of 2,257 kilojoules/kg at 108 degrees C. Industrial systems often operate at pressures in excess of 250 psi. 1 cubic meter of steam can contain enough energy to power a small house. But this energy comes with dangers. Uncontrolled steam is essentially a bomb waiting to explode. This is where our heroes enter the story. Section 2. Introducing the valves. Steam auto control valves are the gatekeepers, the regulators, the invisible hands that tame this powerful force. They open, close, or throttle automatically based on various inputs to maintain precise system parameters. At its most basic, a steam control valve consists of a valve body, a valve seat, a valve plug or disc, and an actuator. But like the characters in your favorite movie franchise, each type has its own special abilities. Let's meet our cast of characters. 1. Globe valves, the reliable all-rounders of the valve world, using a plug-type disc for excellent throttling control in moderate flow conditions. 2. Gate valves, the bouncers of steam systems, designed for full open or full closed positions, creating minimal pressure drop when fully open. 3. Butterfly valves, the elegant performers, using a rotating disc design for quick operation and good throttling in larger pipe diameters. 4. Ball valves, the quick action specialists, featuring a perforated ball that rotates to control flow, ideal for rapid shut-off scenarios. 5. Pressure reducing valves, PRVs, the pressure managers, automatically reducing inlet steam pressure to a controlled lower outlet pressure. 6. Temperature control valves, the thermal guardians, regulating steam flow based on temperature readings from the system. But perhaps the most fascinating is the self-acting control valve, operating without external power, using the very steam it controls to power its operation. It's like nature's own feedback loop, engineered to perfection. Section 3. How they work. Control valve. When we talk about automatic control, we're talking about a feedback system. Simple control loop diagram. Sensor A, controller A, actuator A, valve A, process A. Back to sensor. The system continuously monitors parameters like pressure, temperature, or flow rate, comparing them to desired set points. Any deviation triggers automatic adjustments. Engineering note number 1. Let's see this in action with a pressure-reducing valve or PRV. Control valves operate on the principle of variable resistance. As the valve opening changes, the resistance to flow changes, which directly impacts the flow rate according to the equation Q equals CVA tilde, as I circumflex P, SG, where Q equals flow rate, CV equals valve flow coefficient, I circumflex P equals pressure differential across valve, SG equals specific gravity of fluid. Steam enters at high pressure through the inlet. This pressure acts on the valve plug, pushing it upward against the force of a spring. As downstream pressure increases, it acts on a diaphragm connected to the valve stem, pushing the plug closer to the seat, restricting flow. It's a perfect mechanical balance and no electronics, no computers. Just pure engineering genius. Engineering note number 2, steam capacity calculation for saturated steam through an auto PRV. W equals 22.678 tilde, CVA tilde, PAA tilde, as 1, PA/PAA squared, where W equals steam flow in pounds per hour, CV equals valve flow coefficient, PA equals upstream absolute pressure, SIA, power equals downstream absolute pressure, SEER. The most advanced systems use electronic controllers with pneumatic actuators, offering precise control within a ±1% of set point values. This level of precision is what keeps modern hospitals, textiles, food processing plants, and power stations running safely and efficiently. Section 4, Real-World Applications. These valves aren't just engineering curiosities, they're essential to countless industries. Let's look at where you might find them working tirelessly behind the scenes. 1. In hospitals, steam control valves regulate sterilization equipment, ensuring surgical instruments are properly sanitized at precisely 121 A degrees C, 250 degrees F, for exactly the right amount of time. Too cool, and dangerous pathogens survive. Too hot, and expensive equipment is damaged. 2. In power plants, they manage steam distribution throughout the turbine system. A single modern power plant might have over 1,000 control valves, each one critical to safe operation. 3. In the food industry, they control cooking temperatures for everything from canned goods to dairy products. That perfectly consistent texture of your favorite yogurt, thank a steam control valve. Engineering note number 3, steam trap selection formula, condensate load, pounds per hour, equals surface area, FTA squared, A tilde, heat transfer coefficient A tilde, temperature differential, latent heat. Section 5, when valves fail, the dramatic consequences. The importance of these valves becomes painfully clear when they fail. In 1998, a failed steam control valve at a textile factory in Massachusetts caused a pressure buildup that resulted in an explosion, injuring 8 workers and shutting down production for months. More recently, a 2019 incident at a chemical processing facility was traced back to a stuck temperature control valve that allowed a reaction vessel to overheat. The resulting emergency shutdown cost the company over $2 million in lost production. Engineering note number 4, common failure modes. 1. Mineral buildup, scaling. 2. Erosion of valve seat. 3. Spring fatigue. 4. Diaphragm rupture. 5. Stem packing leakage. This is why valve maintenance isn't just good business, it's a safety imperative. Modern facilities use predictive maintenance techniques, monitoring valve performance with sensors and catching problems before they become catastrophes. Section 6, the cutting edge, smart valves. We're now entering a new era of steam control with smart valves that incorporate IT technology and machine learning algorithms. These valves don't just react to conditions, they predict them. By analyzing patterns in steam demand, temperature fluctuations, and other parameters, they can preemptively adjust to maintain optimal performance. Some advanced systems can even self-diagnose, alerting maintenance teams to potential issues before failure occurs. The valve that sends you a text message when it needs attention is no longer science fiction, it's industrial reality. Engineering note number 5. Smart valve ROI calculation. ROI equals energy savings plus maintenance savings plus downtime prevention. Implementation cost. Industry leaders report energy savings of up to 15% after implementing smart steam control systems, savings that quickly offset the higher initial investment. Conclusion. So, there you have it, the hidden heroes of industrial power. Steam auto control valves, precision engineered, constantly vigilant, silently ensuring the world keeps running. The next time you enjoy a hot shower in a hotel, eat at a restaurant, or visit a hospital, take a moment to appreciate the invisible network of steam and the valves that control it. They're the unsung guardians of our modern world, deserving of recognition for their critical role. Thanks for watching. If you enjoyed this video, please, don't forget to like, comment, share, and subscribe to support the channel. Hit the bell icon so you never miss an update. Share this video with your friends, it really helps us grow. Keep me in your prayers. See you in the next one, coming soon.